Okay, you guys, so this is the last video for this lecture, and in this case, we will be discussing nucleophilic carbonylation reactions. And we talked about carbonylation reactions in the last video and how those were specific to the Stille, the Suzuki, the Negishi, the Kamada, the Custer-Stevens, etc., but not the Heck reaction. The nucleophilic carbonylation reactions are completely independent of all of those cross-coupling reactions. They're in a category of their own. And so let me go ahead and give you the general reaction. Oh, you still need an aryl, vinyl, or alkyl halide or triflate. You still need a palladium catalyst. You still need carbon monoxide because it's a carbonylation reaction. But in this case, instead of needing an alkene, like in the Heck reaction, or a vinyl borane, or an arylstannane tin reagent, or a cuprate reagent, you need a nucleophile. So just as the name implies, you need something that's going to attack a nucleophile. And what you get is a carboxylic acid or a carboxylic acid derivative. So your products are typically carboxylic acids. If your nucleophile is water, esters. If your nucleophile is an alcohol, or amides. If your nucleophile is a primary amine or a secondary amine. Excuse me. Okay. So primary amine or secondary amine. So not surprisingly, there's no ketones. In this case, the nucleophile makes up for the other side of the carbonyl. So it really just depends on what type of nucleophile you're using. Okay. And so let me introduce the general mechanism to this reaction. And then we'll go through examples. And so the mechanism includes, of course, the addition of your catalyst as always. Nothing has changed. We're still using the aryl or the vinyl halide that we need to start with for our oxidative addition step. And just like before, we've got our product and we introduce our carbon monoxide. Complexes to our palladium. Just like before, it does a migratory insertion. Draw. So very similar to what you've seen, right? You're forming a carbonyl compound. It's just that it's a carboxylic acid or a carboxylic acid derivative. So not surprisingly, there's no transmetallation step here, right? There's no transmetallation, there's no rotation, there's no beta hydride elimination. Instead, what happens is a nucleophilic addition. Where you introduce the nucleophile, whatever that nucleophile may be, it adds to the carbonyl. It breaks the bond between the palladium and the carbonyl, and the leaving group pops off. Okay. So, a couple of things before we move forward. Um, at this point, we've got 14 electrons, 16 electrons, 18 electrons, and we're back to 16 electrons. Okay. Once the nucleophile leaves, excuse me, once the nucleophile attacks and the palladium gets its electrons back and the leaving group pops off, we are back at 14 and we have formed our carboxylic acid derivative. Okay. Really clever how it was worked out. So now let me show you a couple of examples with actual nucleophiles as opposed to just a general mechanism. Now, it really depends on what your nucleophile is, right? Um, and for the most part, a lot of these nucleophilic carbonylation reactions are going to require a base. And you'll see why in a second. And it's typically an amine base. Okay. And so we start off with our palladium catalyst. In this case, we introduce our vinyl halide. For our oxidative addition step. Excuse me. So there's my oxidative addition product. I introduce my carbon monoxide. And it complexes, of course, to the metal, to the palladium. It does a migratory insertion. So now I've got my carbonyl, and my carbonyl is now bonded to my vinyl carbon. I've got my nucleophile. In this case, my nucleophile is my alcohol, right? And it's an intramolecular nucleophilic addition. So just like before, follow the exact same arrows. Nucleophile attacks the carbonyl. The bond between the palladium and the carbon is broken. The electrons are given back to the palladium, and my leaving group pops off. Same thing. Nucleophile attacks the carbonyl. Bond between the palladium and the carbonyl is broken, and the electrons go towards the palladium, and my leaving group pops off. Now, you're obviously forming a ring. It's an intramolecular nucleophilic addition. Again, intramolecular meaning it's all occurring in the same system, right? So if you number your atoms, you realize that because oxygen 5 is attacking your carbonyl 1, you are going to form a 5-membered ring. So not only do you regenerate your catalyst, but you're going to form a 5-membered ring. And if you need to continue to number your carbons, then by all means do so. And your oxygen. So this is a cyclic ester, also known as a lactone, or a precursor to a lactone. I've got a positive charge, so how do I get rid of that positive charge? I use the base to deprotonate, and now I can form my desired lactone product. And lactone is, of course, just a cyclic ester. Okay? So really clever how it was thought out. Okay? Let's do another example. Now, this example can feel a little tricky because I previously mentioned that, hey, for these nucleophilic carbonylation reactions, these are really popular for carboxylic acid formation, esters, and amines, right? But you can pretty much use anything as a nucleophile. I've seen people use enolates as nucleophiles. I've seen people use alkenes as nucleophiles. So really you can use anything. Enolates, which would of course form ketones, but you can also use alkenes. Really clever the way they've expanded on this work. And so this next example will have an alkene nucleophile. Okay, so this is our product. Notice that we've got our vinyl halide, our alkene nucleophile, our carbon monoxide. we've got our base. Notice that even though this is our base, this can't be our nucleophile, right? It's a tertiary amine. There's no carboxylic acid derivative that has four bonds to a nitrogen. So it's just acting as a base. Okay. So let's start off just like we did before with our catalyst and our oxidative addition step. I'm going to draw it a little differently just so that I can have space. I know I usually draw my oxidative addition step on the right, but I just want to keep it consistent with my starting material. And so if you notice, I've stayed consistent. I don't want to move things around or flip things around and just confuse myself even more. I add the carbon monoxide. Just like before, you do a migratory insertion. I want to make sure that I have enough room for everything I want to draw out. So there's my migratory insertion product. Again, my alkene is my nucleophile, right? You learned this in sophomore organic chemistry. Alkenes can attack halogens for dihalogenation. They're great nucleophiles. They can attack acids. They're thought of as the base. So just like before, alkenes are going to react as nucleophiles in this case. Now, I need to figure out which is going to be my nucleophilic carbon, carbon 1 or carbon 2, right? Because I know my double bond is going to attack my palladium and my halogen is going to come off. That's nothing new. I'm going to generate my catalyst, nucleophilic addition. But there's really two possible products that I can get. And so let's go ahead and draw out those two possible products. The first product is, of course, the following. And I'll try to keep it as I've drawn it. Okay. Where carbon 1 is what's bonded to carbon 6, and my positive charge is at carbon 2. Right? Or, so notice how carbon 1 was the nucleophilic carbon. Or if carbon 2, sorry, is what attacks carbon 6, then carbon 1 has the positive charge. And now it's become a substituent, and I have formed a 5-membered ring. So which one is the most favored? Well, 5 and 6-membered rings are pretty stable, right? They're they're both favored in that sense. But this is a secondary carbocation, and this is a primary carbocation. So not surprisingly, the secondary carbocation is the more stable, right? You learn this in SN1, E1, the more substituted the carbocation, the more stable. Primary carbocations are just simply unlikely, okay? So this is the product, or this is the intermediate of the product. I'm not done yet, right? I still need to come in and bring my base, which is triethylamine. I think it's triethylamine. And it does an elimination. To form the desired product. Here's a question for you. Why didn't my triethylamine deprotonate at carbon 3? It's also next door to carbon 2, so why isn't that favored? Why isn't that favored to form the double bond there? Okay. So despite carbonylation reactions allowing the expansion of a chain or a ring by 1 carbon, there are drawbacks to it, right? If you're using carbon monoxide, it's poisonous. Um, it's a hazardous gas, right? Typically, when you use carbon monoxide for carbonylation reactions, so let me say gas, you typically need to run the reaction at high temperatures and high pressures. And because you're running it at high temperature and high pressure, I don't know if you guys have seen this before, but you typically run the reaction in a stainless steel vessel. Also known as a bomb. That's literally what it's called. And so there's this really high risk of overpressurizing, chemical exposure, and of course, fires. And so despite the fact that it's just such a really great reaction, the drawbacks to it are just really not quite worth it. But recently, uh, I won't introduce the methodology. This is just a highlight of the methodology. Recently, groups have been using formic acid and acetic anhydride to form the following derivative. So, in the presence of formic acid and acetic anhydride, which are all cheap starting materials and don't need high temperatures, high pressures. Um, they're not poisonous. You can form the following derivative through a carboxylic acid derivative reaction. And what they found is really clever. You don't need to use a high pressure vessel. You form this derivative, and if you just redraw it, what they found is that it rearranges to form carbon monoxide gas and acetic acid. And so it's really clever because you don't have to add all this excess gas and pump all this gas into your reaction. You can just use these two liquids, form enough carbon monoxide to set up your reaction, and your only byproduct isn't more carbon monoxide, it's just an acetic acid that you can neutralize in the end. So really clever are the advances that have come from troubleshooting these carbon monoxide reactions. Okay, you guys, this is the last part of this lecture uh, series. Next week will be your midterm number 2. And I'll go ahead and send out announcements about that as well.